So now I want to introduce Hall's marriage theorem. So the idea here is we've got a matching problem, as we've been discussing before. So we've got a set A of people, set B of jobs, and these are going to be finite sets as usual, and a set CB subset A of qualified people for each job. Okay, and we've been discussing the problem of counting a number of possible ways of doing partial matchings or full matchings, where we assign assign people to some subset of the jobs. But we might not actually care about counting the number of solutions. We might just want to know whether there are any solutions at all. And in that context, there's some different methods that we can choose, that we can use, and that's what Hall's marriage theorem is about. So to explain what's going on there, we're going to extend this notation a bit. So for a set U, say B1 up to BR of jobs, we're going to put CU is union of the candidate sets. Okay, so this is the set of people qualified for at least one job. In U. Okay. So obviously we want these sets to be big, right? If there's lots of candidates for each job, or lots of candidates for every combination of jobs, then that's going to make the problem of assigning people to jobs easier. So we're going to be interested in the size of these sets CU. So we're going to define the following concept. We're going to say that U is plausible if the size of CU is at least as large as the size of U, and U is implausible if the size of CU is strictly less than the size of U. And then we're down. So this is a key idea. It's going to turn out it's going to be fairly straightforward to show that if there's an implausible set, then it's not actually possible to solve this allocation problem. Okay, so let's write that again and just extend the notation slightly. So, so I'm going to say that U is very plausible if the size of CU is strictly greater than U, the size of U, and barely plausible if the size of CU is just equal to the size of U, and plausible if the size of CU is greater than or equal to the size of U. So it's plausible if and only if one of these two conditions holds, and implausible if the size of CU is less than the size of U. Okay, we'll just illustrate this with an example. We're going to have an example here with 5 people and 5 jobs. Okay, so people are going to be called P, Q, R, S, T. and the jobs are A to E. And then the kind of chessboard type diagram is going to be like this. Okay, so there's our chessboard diagram. Okay, and so let's consider various sets. If we look at so we could have our U could just be set containing E, and then what's CU? So here we've just got E, and then you want the CU is going to be the candidates for E, so that's going to be these two people here, Q and S. And so so here obviously the size of U is 1 and the size of CU is 2, so this one is very plausible. We could instead look at the set maybe what do we want to do next? We want to do AB. Okay. So what are the candidates for A and B? That's the set of people who can do at least one of those jobs, but A and B seem to be quite easy jobs. Lots of people can do them, and everyone except for Q can do job A, but Q can do job B. So the candidates for A and B is just everyone. So we've got size of U is 2 and the size of CU is 5. So that's again very plausible. Now let's look at the set CD. Okay, so who are the candidates for C and D? Well, S can do both C and D, Q can do C. No one else can do either of C and D, so this is just Q and S. So the size of U and the size of CU are both 2, so that's barely plausible. But if we look at CDE, okay, people who can do any of CD and E, well, again, so it's the same answer again, right? Q can do C and E, S can do all of CD and E, but no one else can do any of these jobs. So we've just got QS again. So here we've got 3 jobs and only 2 candidates, so this one is implausible. And this causes a problem. This means that we can't actually solve this allocation problem, right? Because we've got to assign these jobs C, D, and E to someone. We've got to assign them to people who are qualified to do them. But the only people who could do any of C, D, and E are Q and S, right? So we've got 3 jobs, and there's only these 2 people, Q and S, who could possibly cover any of these jobs. So you've got 3 jobs and only 2 people to cover them, and no one's allowed to have more than 1 job. So that proves that the problem cannot be solved. Yeah, so that line of argument that we just explained, let's formulate that a little bit more carefully and more formally. So a proposition like this. If the matching problem is solvable, then every subset U is plausible. So just recall what that meant. That meant that the number of candidates is at least as large as the number of jobs. And let's just record the contrapositive of that statement, which is a completely logically equivalent statement. If some subset is implausible, a problem cannot be solved. Okay. So that's our claim. Okay, we're going to suppose that we've got a solution, and then and let's consider a subset, say U, which might be B1 up to BR. Okay, so we're assuming we've got a solution. Solution must assign each job to a person. Okay, I guess wasn't completely explicit about this. We're in this section we're considering by a solution we mean that every job has to be assigned to a person. We're allowed to have unemployed people, so not every person has to have a job, but every job has to have a person. Okay, so we've assigned all the jobs in B to appropriate people. So in particular, we've assigned each of these jobs B1 up to BR to someone, and so we're going to say AI is the person who's assigned job BI. No one has more than one job, and that's kind of part of the rules that we're assuming here. That well, when we talk about a solution, we mean a solution that follows the usual rules, and so it doesn't give more than one job to the same person. So these people are all different, and also AI and one of the other rules that we're assuming for a solution, by a solution we mean that every job gets allocated to a qualified person. So AI must be qualified for BI, so that means that AI is an element of the candidate set CBI, which is a subset of the union. And remember that this was the definition of CU. So these are distinct elements of CU. So the size of CU is at least as large as R, which is the size of U. And that's what we were supposed to be proving. Okay? So, so if there's a solution, then every subset is plausible. And so by contrapositive, if there's any implausible set, then that proves that this assignment problem can't be solved.